All right. Are we ready for some C++ then? Okay. Well, here's what we'll discuss today. So, when faced with OO problems, many C++ programmers think that means you have to use inheritance and virtual functions, but that's far from the only way to do it in C++. And some of these other OO techniques are often a better choice in practical programs. This talk will cover three approaches that cover most use cases, and I find myself using these again and again. And inheritance and virtual functions, we still use them sometimes, concepts, and variant-based polymorphism. So, first of all, what is OO? Okay, spoiler, it's object orientation. All right, but that's begging the question. What is object orientation? Spoiler, nobody has any idea what it is. So here's a quote from Benjamin Pierce's Great Types and Programming Languages textbook. Most arguments about what is the essence of do more to reveal the prejudices of the participants than to discover any objective truth about the topic of discussion. Attempts to find the term object-oriented precisely are no exception. So what will we do with this talk? Yes?
Isn't there also one more like object-oriented type of programming style that you did not mention? The phrase recurring template pattern?
Yeah, I'll mention briefly that you can use CRTP to do static polymorphism, but there are actually better solutions to the same use case in modern C++. So I'm just going to, I'm a simple man, so to me, object-oriented means oriented around objects. And when we need to operate an object, we'll ask the object to perform the operation. And what and how it does it is none of our business. And typically we'll do this by calling a method on the object. So I'm going to assume you've worked a little with C++ classes, but just to remind us, methods are defined as members of the object's class. So here we have two members, foo and bar. They return a string. They're members of class A. I have a class A object named foobar, and I print its foo and its bar, and it prints foobar. But here's the interesting question that maybe isn't as well known is, what is the actual class of the object? And I think this gets to the heart of object orientation. An expression in C++ actually is two types. The type of the expression, which is sometimes called the static or the compile time type, or the type of the actual object in memory, which is called the dynamic or the runtime type. And these can be different, and that's called polymorphism. And they mainly can differ because of inheritance. And we'll see an example below. So which class do you find the method that's called in? Well, the philosophy of most languages is the language makes that decision to you. Languages that build themselves as object-oriented, like Java, always use the dynamic type to find which method to call, where languages that aren't object-oriented, like C, always use the static type. So they use the type of the expression in the code. Well, that's not the philosophy of C++. C++ says the programmer chooses. Since both are usual, C++ supports each, and non-virtual methods use the static type, virtual methods use the runtime type. Let's illustrate this with an example. So here, I don't know how readable this is in back, but we have a struct animal, which is function, a method F and a method G. G is virtual, F is not. And gorilla inherits from animal. It redefines F and G and it adds an H. Now I create a gorilla object G and have an animal reference A that refers to that same gorilla object. Well, if I call A.F, is this going to call animals F or gorillas F? Right. And because the A is an expression of type animal reference and F is not virtual, A.F is going to be animals F, and that will print animals F. What about A.G? Yes, gorilla, because G is virtual, and it cares about the type of the actual object in memory, not the expression A. What about A.H? Right. A has no H. It doesn't matter that gorillas have them. So that's ill form. If I call G.F, G.G, and G.H, yeah, the dynamic type and the static type is gorilla in both cases. Yeah, you can annotate it and stuff like that, but that would have given away the answers to some of the questions, and we don't want that. So here's a good question though. Maybe Java got it right. Why not always use virtual methods, right? And in object-oriented languages, all method calls are virtual. In fact, I'll use OO without quotation marks to refer to this familiar object-oriented style of using inheritance and virtuals. Well, is there anything wrong, right? C++ would never add any complexity that serves no purpose, right? So let's see. Okay, well, why not always use virtuals? Well, one reason is performance. So you may have heard that virtual functions only have one more direction, and you don't need to worry about their performance cost. And this is indeed mostly true, but what's not so well known is it's not always true. Well, let's look at an example that I just happen to have in my IDE here. So here I have a function that I'm calling 100 million times. What's wrong here? Share this whole screen. Actually, I will try. Okay. Zoom has a little bit of trouble with that. So you see here, I'm going to create a object and call its F method 100 million times. And I'm going to increment the second argument. And here's what my F looks like. It just does a little bit of arithmetic. It's first argument times the log of the first argument times the second argument. And I made everything an int because logs aren't always ints. Okay. And now I'm going to go ahead and try to run this. And let's see how long it takes. And by the way, F is virtual. All right. So now I'm going to run it, and it takes half a second to run. Let's see, does it get any faster if it's not virtual? Let's try it again. It still takes half a second, right? Virtual is cheap, adds negligible overhead. But let's try a slightly different version of this program. This one differs only, instead of incrementing the first argument, I'm incrementing the second argument. Let's see if that makes a difference. Well, it's virtual now. It takes half a second roughly to run, like we're used to. Let's make F not virtual. Try it again. There it is. It's 12 times as fast by not being virtual. Well, what happened?
Part of it is that the pilot kind of optimized how
Yeah, let me go and take this here. The main performance cost of virtual functions isn't the cost of the virtual function call, it's the loss of visibility to the compiler optimizer. And in the second benchmark, log 10 really only needed to be calculated once, but if it's a virtual method, the compiler doesn't know what will be called. So it can't hoist the transcendental function out of the loop, and we're calculating it 100 million times. So it's usually isn't significant, but it's good to understand that the more virtual functions you use, the less visibility the compiler has in your code to optimize it. So here's another reason not to use virtuals: polar bears, right? Java programs use 50% more energy than C++ programs. I have a link to that here. In fact, while modern Java jets do use dynamic advanced devirtualization technique, deferring all dispatching until runtime is likely a big reason why you burn more carbons. So one particular call doesn't make a difference. But when you're doing trillions of them, just think of the polar bears, right? Another reason to not always use virtuals is interoperability. Code that needs to interoperate with other languages needs data types with a fixed layout in memory. And in fact, C++ provides a type trait called is standard layout for this to check that. And as soon as you introduce virtual methods into the equation, the compiler starts putting secret fields in the type to help the runtime system figure out what method to call, and you no longer have control over the object layout. Another reason is verifiability. All right, just like virtual methods will confuse the compiler's optimizers, they'll confuse code coverage tools, static analyzers, model checkers, and the like, that are there to ensure that your program is safe and reliable, even though it's written in a low-level native language. Here's another reason not to use virtuals. Anybody ever hear of spaghetti inheritance? Yeah, so in inheritance-based object orientation, a class needs to inherit from every possible thing that it might need to override. And this goes against, who's heard of the solid principles? Yes, some of you. That would be a whole lecture in itself, but it's a standard set of best practices for organizing object-oriented code, and the I of solid is the interface segregation principle that says many client-specific interfaces are better than one general-purpose interface, which means all your classes are going to start inheriting from a whole bunch of things, and multiple inheritance, and virtual inheritance gets to be a mess that's hard to work with and maintain really quickly. There's another reason why virtuals don't cut it. So let's suppose you're writing a game that uses a library of animal classes that someone else wrote, like my animal and gorilla. Now, you might wish each animal had a virtual hit points method, because that's exactly what your game needs. But of course they don't, because the designer of the animal hierarchy doesn't know about this game you're trying to write. And this happens a lot, what you do. And again, if you're familiar with the solid principle, this is an example of the O, which is called the open-close principle, which is you want to extend the class's behavior, they're open, but you don't want to mess with the classes, which means they're closed. And virtual functions don't fill that gap between being open and closed. So what's our best practice here? Okay, I'm not trying to scare you from using virtual methods. Usually that's fine. The performance costs almost always minimal, and the availability for runtime dispatch is very powerful, and compilers optimize virtual methods really, really well. But don't use virtual functions for no reason, right? Gratuitous use of virtual function can impede compiler code optimization, unpredictably modify memory layout, impede program analysis and automated reasoning tools, lead to unmaintainable spaghetti inheritance, hierarchies, fail to meet the needs of client-side extensibility, and of course, kill the polar bears. So let's look at maybe what are some other approaches that we can take. Well, one that's worth noting is that templates and object orientation can solve similar problems. And here's a great quote from Bjarne that generic programming should just be normal programming. So how would I use templates instead of inheritance and virtuals? Well, let's look at a real world example. Suppose C++ didn't have mutexes, and it didn't until C++ 11. So how would we design them? Well, we'd probably begin by looking at how Java does it, right? And Java uses inheritance and virtual methods. Something like this, which I'll write in C++ syntax, there's some kind of lockable abstract class with a lock and unlock method. And there's a mutex struct that overrides it with implementations of lock and unlock that work on the concrete mutex type. And now I would have a lockguard class that has a lockable reference member, and the constructor will lock it, and the destructor will unlock it. So how would I use this Java-style mutex? Well, at the beginning of my function that wants to access protected data, I'd say lockguard LK of my mutex. And then when I leave, the destructor of LK will unlock it. And this is exactly what C++ code looks like, right? As far as we know, this is implemented in a Java style. But of course, you're probably saying, wait a moment, that is not how C++ mutex actually work. There is no lockable base class for them to inherit from. And in fact, we use templates instead of the virtual override approach. And since mutexes are frequently used in hot code, this seems like a really good decision. Let's take a look. So in C++, I don't bother inheriting or having virtuals, right? I just have to have a lock and an unlock method, and lockguard is no longer a class, it's a class template. So instead of holding a lockable reference, it just holds a T reference, where T is whatever the type is. And what does the client code look like? It looks exactly the same as before, only it's more performant and our class hierarchies are simpler. One thing to note here is because of class template argument deduction, you don't even need to explain you're using a mutex because it recognizes T from the constructor. Okay, so this has been worked that way since C++ 17, and concepts in C++ 20 make it even better, right? Because C++ 20 concepts lean in to the analogy between templates and traditional object-oriented techniques. So let's look at this animal example with virtuals. So here I have my animal again. I've given it name and eats, and cat and inherits from animal and overrides them, right? So now I have a program where I can have a unique putter animal and have it reference a cat, and now it can say a cat eats mice, right? And we are good. Do we need to actually use inheritance, virtual functions, the non-quotation mark O's? Not really. I could have just written a cat class. Now say auto A equals cat, and all my client code can use A oblivious to what particular kind of animal it is. Right here, I didn't even use templates. But this isn't a very good way to write code because we lost any kind of understanding that A is an animal, right? A could be house or ant, and we might not find out that something went wrong until much, much later when we did something that depends on A being an animal. So what we need is a way to codify our expectations for A. So we're warned if we did the wrong thing without all the overhead and complexity of creating these base classes. And that's what concepts do for us, right? So the concept explains what you can do with a particular type. And here we can create an animal concept that requires you can ask what it eats and you can ask what its name is. And there's notation for it that you learn, but it's pretty straightforward. So now we can ensure that I'm working with an animal or something that satisfies the animal concept, that is. So if I say animal auto A equals cat, if cat didn't have an eats and a name method, the compiler would tell me, wait a moment, this is not an animal. But fortunately it does, so this code runs okay. So let's compare the two cases. Okay, as you can see, here's the virtual function version. And here's how I defined the class. I had to list the inheritance. I set the overriding. And now I wrote the code and it worked. Here I create the concept, but then I create cat straight away. Animal auto A equals cat ensures me that I've got an animal, and then you see both of them produce the same output. So generic programming can just be normal programming, right? Pierre was right. Now, how does this compare? Well, performance is better not so much because of the elimination of virtual functions, but because I no longer have to do a memory allocation to create the object. It's directly on the stack. And by not needing inheritance, it makes it easier for us to use our classes wherever they're appropriate without having to create complex inheritance hierarchy. Now, there's a little bit of a type safety cost where, right, Pac-Man isn't an animal, but it does eat, as we all know. So a more serious problem is the lack of runtime polymorphism here, right? Suppose I wanted to create a zoo and I want a set of animals. Well, that doesn't work if animals just a concept, because I can't have a set of all sorts of different types. But if I have an animal-based class, I can say set of unique put-or animal will be my zoo. So let's see if we can come up with some guidelines on what to choose. Okay. So there's often a choice between base classes and virtuals, and templates and concepts. And in fact, other choices we'll learn about in a few minutes. So how can we make sense of all the possible different approaches? And there's a problem we'll want to understand a little better, which is this client-side extensibility problem. Now, suppose you're using a class hierarchy and you wish the classes in a virtual method that was specific to the needs of your application. For example, you're writing a game and you want to give each animal this hit points method. And whoever wrote that crappy animal hierarchy didn't put in those hit points that your program needed because they didn't read your mind, right? And even if you could, you really want to clutter up a general purpose animal interface with individual things about your application. So there's something called the visitor pattern that you can use to inject your own virtuals into existing classes. So suppose as a user of the animal class, I want to inject this hit points virtual method. Well, the one thing the author of the animal hierarchy has to do is create a visitor class that's abstract and can be overridden. So we have the animal visitor that knows how to visit a cat and a dog and whatever types we know about. And then they have to have an accept method to each animal, right? And you can treat the way this is written as magic words. Well, now, if I'm the class user, I can go and explain what I want the virtual method to be, okay, by declaring my own hit point visitor that inherits from animal visitor and says if I visit a dog reference, I'm going to set the hit points to 10, and if it's a cat, I'll set them to 12. Well, now I can get the hit points of animals, and except for this except notation, it acts just like that was a virtual function built into the type from the beginning. Because when I say a arrow accept of my hit point visitor of HP, the virtual override of accept is already in the actual dynamic animal type. And that calls the thing you overrode for cat. Yes? Oh, just some jerk, right? So the So this calls cat's hit point function that we put in the hit point visitor up here. You see, this is the version for cats. So it uses the dynamic type of your object, just like virtuals do. So as a best practice, if you're designing a class hierarchy, unless the interface for it is absolutely clear that this is the perfect interface for everyone who might use this hierarchy, add this except method as customization. Okay, let's talk about another approach, which is using duck type variants for performant extensible OO. Well, first of all, what do I mean by duck type? All right, that's not it. I gave a talk on this in Shenzhen once with real-time translation. I felt really bad. That slide. But anyway, there is a saying that if it walks like a duck and it quacks like a duck, then it's a duck. And by duck, I mean a C++ type, right? So the idea is inheritance models ISM, right? So inheritance explicitly says which interface you're supporting. This is sometimes called nominal typing in the integer. Duck typing gives a different notion of ISM. If the class is a walk method and a quack method, let's not worry about inheritance or anything else. It walks and it quacks, it's a duck. And this is sometimes called structural typing in the literature. But duck typing is such a better term, right? So this should be familiar to C++ programmers because templates have always used duck typing, right? Here I have a squaring function template that can square an int or a double or a matrix or anything else that does it. And it doesn't require that its argument inherits from is squareable or has multiplication. It's just enough that this code makes sense to use here. Now, the problem is if you don't say anything about what's needed, you could quickly end up where you don't know what you're working with. So concepts are really designed to prove this. And if necessary, we could create a has multiplication concept or whatever the requirements are for my thing and use that up front without having to modify the existing class hierarchy. It's going to all be done on the outside. Now, C++ templates have always been duck typed, and duck typing is really nice, but they also have this limitation we mentioned that they have to be dispatched at compile time. So the compiler needs to figure out what the actual type is, right? And that's why I couldn't say set angle brackets animal if animal is a concept, because it's really a set of many different type objects, right? So because duck typing is flexible and forgiving and more loosely coupled, while we're still remaining with a good degree of static type safety, people have asked, could we use something that's as dynamic as inheritance and virtuals, but duck typed instead? So C++ 17 introduced a variant abstraction that generalizes C unions. And the idea is a variant AB can hold an A or a B, but not both at the same time. And these variants will be the basis of an approach to OO that will be more dynamic than our animal concept, because we can change what type of animals, store them all in a single container. Everything will be value-based, So I no longer need to worry about unique putters, object lifetimes, RAII, and all of these other advanced C++ techniques that you may or may not know about. It's often is much better performance than inheritance virtual object orientation because A and B don't need to be allocated dynamically on the heap. They're just values. Okay, so first, what's a variant? Well, a variant is a lot like a tuple, right? But instead of holding all of its fields at once, it only contains one of them at a time. So its interface looks like tuple. I can say, get the 0th index or get the first index because V is a variant of an int and double. Okay, but I put the int 3 in it. So if I get the 0th index, I'll get a 3. If I try getting the first index, it'll throw an exception because this variant is currently holding an int, not a double. Of course, if I say V equals 3.5, now it's holding a double and not an int. And you can also address variants by type. So say getting the brackets double of V, and you can query which particular thing is in it and does it hold a particular type alike. Okay, well, suppose we happen to know all of the animal classes at compile time, and it's very likely that we do because you can't create new classes after compile time, right? So if that's the case, we could just say an animal is something might be a cat or it might be a dog. Well, that sounds like a variant. So we can say using animal equals variant cat dog. Now, variant cat dog is a great way to store something that could be either a cat or a dog and could even change its mind later, right? And store a different one. But how can I do something like the name method? Well, the standard library is a solution that stood visit, and please don't confuse this with the visitor pattern we just discussed. While it's related, it's not quite the same enough to be anything other than confusing. So if V is a variant and C is a callable, then visit of CV calls your callable thing C with what's actually stored in V, the variant V. So does this solve our problem of making variants behave like virtuals? Well, let's see. Well, here, the animal A, that's a variant cat dog, but right now it holds a cat. Now I'm going to visit it with something that can take an auto-reference, which means X will be a type cat reference or dog reference, depending on whether A held a cat or a dog, and it'll call the name method. So it'll call cats' names or dogs' names based on the dynamic whatever is stored inside the variant. And that will print cat just like we want. Now, the problem is this notation is really cumbersome to use. So typically we encapsulate this in a helper function. We can take a little bit of a look at this code. By the way, normally forward references are just the bane of C++ programmers, but they work really well with variants. So that's, I mean, I did have to say class cat or class dog, but you didn't need to do anything. But so now I have my cat class, dog class, no need for inheritance, no need for virtuals. I'll go put the visit in a name and each helper function. And look at this, we have our old example back again. And this uses the dynamic type of whatever is in A. Now, I'm going to go through all this and I'll take some questions on it. Okay. So in some ways, this is really the best of both worlds. It's almost as fast as templates, typically way faster than inheritance and virtual function because it skips that memory allocation. There's no brittle inheritance hierarchy, but you still have a lot of type safety, but it's as dynamic as traditional object orientation. And a set of animals is a great way to do a zoo, unlike our concepts version. So this is even simpler than the much wordier set angle brackets unique putter animal approach required by the traditional virtual method almost. Okay, so another thing I want to point out about this example is virtual functions introduce a lot of brittleness into your code because when you override a function, you have to exactly match the signature, right? And that can be very constraining, and in any case, it's a headache. So here, like if I wanted to inherit cats from animal and override eat, where I could put in, because apparently cats do not just eat mice, right? Like they seem to eat my finger, for example. And so I'd like to be able to pass in a prey for it. And I'll give it a default value of mouse, so I can just call eat if I want. And you'd think that would be perfectly good override, because I can call it with no arguments, but no, the compiler will not let you do that because it's not an exact match for what it's overriding. But in the very visitor version, well, our visitor that we call visit with is just going to call eats with no arguments. And as long as that's a valuable call, valid call, you should be okay. So in this case, it'll eat a mouse because it's calling it with no arguments. All right, what about client-side extensibility? Well, just like we discussed with the visitor pattern, users of the animal type can add their own methods. So to do this, we're going to use a really cool pattern called the overloaded pattern, right? So the first thing we're going to need to do is define an overloaded class template, but you only need to do this once in your entire life, right? It's always the same. So the overloaded class template has a bunch of template arguments, and it inherits from all of them, okay? And it's also going to want to inherit all of their function call arguments, but because of C++ is funny hiding rules, we're going to just have to pull in the function call arguments of what it inherits from. But this whole thing you write at once. So now let's create an implementation of hit points like we did before. So we created an overloaded object named hit points. And now we just give its implementations, all the things we're inheriting from are actually different lambdas, and we're inheriting their ability to be called. So now if I call hit points with the cat reference, this one will be the best fit, right? If I call it with the dog reference, this one will be the best fit. And now I just say visit hit points on A, and it prints 12, right? Now again, I don't need to it to give the template arguments for overloaded. Why not? Because class template argument deduction doesn't for me, and that's really helpful because there is no actual name in C++ for the type of this lambda. Okay, and go ahead and have one of these scaffold things here, and it actually figured out it's a cat. It has 12 hit points. It's still healthy, hasn't begun to go through its 9 lives, etc. Okay. Now, I will want to point out that duck type variants are not perfect. Right? It's just one more strategy in your toolbox. Well, first of all, while the flexibility is nice, right, the types are a little more relaxed, right? You can't tell that a shape straw method for drawing a picture is different than a cowboy straw method for drawing a gun, right? So variants always use as much space as the biggest type also. So this could be really inefficient if you have one really big animal type with 1,000 fields. And also, whenever we create a new kind of animal, we have to add it to the variant and recompile the world to do that. So that can create a bunch of maintenance problems. So, and then, I think I skipped the first bullet, but frankly, in practice, it's the one that bothers me the most. There's no built-in language support for this yet anyways. So you have to deal with a bunch of uglier library interfaces to do it. So because it's ugly and not well known, I only use variant-based polymorphism instead of virtuals or concept when there's a clear benefit. And in practice, I do use it a lot, but I use it less than I do virtual functions or concepts. So how do I know what to use? Well, the following table is admittedly oversimplistic, and somebody's going to be like, well, that's not really right and all of that. Yes, I know. But this is kind of the checklist I keep in my head and usually helps conform the decision, right? So virtuals and concepts have nice native language support. Concepts and variants get the best performance. Can things be dispatched at runtime, or does the compiler have to know the type? Well, concepts, they need to be resolved at compile time. The other two are dynamic. Do they support duck typing? Well, concepts and variants do, and virtuals don't. Can I work with values instead of make uniquing everything? Well, sometimes I want one or the other. So, but if I want value-based, then concepts or variants do the trick, and they all have their own extension idiom. Why didn't I explain it for concepts? Well, you get extension for free with concepts. They're just templates. So, let me go here. Now, as you mentioned at the beginning, well, I've covered about 3 approaches to writing code for solving object-oriented problems in C++: inheritance virtuals, concepts, invariant-based polymorphism, as well as giving a couple of client-side extensibility mechanisms, the visitor pattern and the overloaded pattern, right? As you pointed out, there are a bunch of more. In particular, you may be familiar with other techniques like static polymorphism, which relies on, this very either cool or insane or both curiously recurring template pattern, or pre-C++ 20 template techniques like Spinny and Voight. The good news is for the most part, these C++20 solutions that I've discussed are better. And if you learn these approaches, you should be well equipped for most object-oriented programming, and then pull in other techniques when needed, like when you're maintaining legacy code, or if you really need nominally typed static dispatching, you might need to learn the CRTP-based static polymorphism. But that stuff requires a whole lot more boilerplate. It's mostly unnecessary now. Similarly, concepts replace spin A and void T and stuff like that. So I do want to give a little bit of teaser here, because I did say for the most part. So there is one other technique that's good for going and dispatching based on types, called type erasure, that we don't have time to cover today, but does deserve to be part of your toolkit. And depending on which side of the bed I wake up on, I like to think of it as either like a way to virtual functions without a common base class. And it replaces inheritance with something called the type erasure model. Or I like to think of it as a variant of who knows what types will be in the variant, right? Now, the price you pay for this is this requires a lot of boilerplate to set up, and it's significantly more complicated than the techniques I discussed here. And I'm not going to cover it right now, but fortunately, Mr. Douglas over there is a great presentation on type erasure on YouTube, or even better yet, maybe we can get him to present it here sometime. All right. Thank you very much. And now I think we do have some time for some more questions. I know you've been waiting patiently. You go first.
So I actually have a couple of one is like probably required that you got the program to really
Okay, first, it's very possible I forgot a semicolon. Right, seriously, the only thing that's really hard about C++ is figuring out where you put the semicolons. So it's perfectly possible I got that right. So yes, I think as of C++20, variants are const expert. I don't really know why you use a variant for purposes like this if you're only interested in static types. So, you use them to fuel const X for functions. But if I'm really just trying to do object-oriented design of my program, and I'm happy with static dispatching, I'll just use concepts. So I think that really helps this use case that much. I think April had a question.
That sort of mirror an existing virtual base class, where, so in the circumstances where you want inlining to be possible, like for and to have static dispatch, you just have something with the concept, but then you also have this virtual base or this abstract base class that has the same interface. So if you keep the reference one, do you think that's a
Yeah, so what?
There's a request to repeat the questions.
Oh, request to repeat the question. So this question, you can tell me if I got it right. is sometimes you like to use concepts, but also kind of give a base class with the same idea as it. So you can get really good static dispatching in your code where the compiler can deduce the type. And you could also still have a set of animals or something like that where it may be dynamically based at runtime and heterogeneous types and all of that. And I think you can do that, but I don't think there's consensus yet on how to get the idioms right. And if you dig around in the WG21 site, that's the C++ Standard Committee site, you could see a proposal that I did maybe about 2018 or 2019 that said, what if you wanted to use a class as a concept? And its meaning would be that class is like a base class for those things. That is not in the language, I should tell you. But I think eventually we're going to figure out what is the right idiomatic way to do exactly what you say. And that'll be really useful. But right now, everybody does it their own way. And we don't really know what's best. Here, you way back.
So you had one of the principles was that you couldn't extend that class that you would get from a library. So I'm trying to understand the case of the hit points example. Why wouldn't you extend the class that is in the library on the series final? But why don't you just extend the class that is in the library and include an universal method that has?
Okay, now I want to repeat this because the question is, you know, wait a moment. Classes are designed for extensibility. You can just inherit from them and then add your own methods that you want. Now, the problem with that is, yes, it's easy to inherit from a class, but it's very hard to inherit from a class hierarchy, right? Because I want my cat to inherit from my animal and, you know, so forth. So I'm going to have to build an entire parallel hierarchy. And you can do that, but it's really hard, right? Like, for example, the author of the original hierarchy has to use virtual inheritance everywhere, which significantly restricts what kind of casting you can do and a lot of other things. And in general, while it's easy to extend a class, usually you get an inheritance hierarchy. And it's very difficult to inject a new method into them. So the accept idiom works a lot better in that case. Okay, you.
So one downside is that this coincides with combination products. So if we had any
So, yeah, so the question is, one downside of templates is they increase your compilation time and can make your code much bigger. And that is true, right? Like, I remember one time I had like a 200-line section of a program I was doing at work that took 8 hours to compile on the company built for it every night. And like the other million lines of code only got 2 hours to compile. Needless to say, I was not very popular and had to buy a lot of donuts. But the fact is, at that time, people didn't really understand like the pervasive power and ability of templates, and compilers designers now do a ton of work on making templates much more efficient. So can it be a problem now? Absolutely. But is it a problem now? Much less frequently than it used to be, right? Like there was the day when people argued whether you should have template-based containers or object-based containers and stuff like that. Now everybody's like, thank God we have template-based containers. So for the most of the cases you'll run into, that shouldn't drive the decision. By specific cases, it may become a consideration, and you should keep your eye open for that. Okay, you.
Yeah, so I was just wondering, for the variance kind of, if you actually wanted to spin that, let's say that you had like a different animal type, and you wanted to add one more, but you probably had these and the main method. Would the compiler suggest explode, or what would be the compiler check to make sure that we not or that we have those methods inside the code?
Oh, well, the point is you can store it in an animal autoreference, and that will, the compiler will say, as soon as you created the object and you move it into the animal world, it'll say, wait a moment, it doesn't satisfy the animal concept. Right, fundamentally, templates were really useful, but completely broken until concepts came around, right? And, you know, but they were still like, even then, it was like way better to use template-based containers than object-based containers, but they're so great. But now you get them without the downside, is that you can annotate what operations you expect via concept, and the compiler will check them right away. So concepts are fantastic. They're like much better and much more important than anything I talked about here, other than this narrow application of concepts. So I encourage you to learn about all you can do with concepts. Yes?
Can you explain a little bit of the overriding example? Because those are a little bit interesting. You can spend 1 minute explaining the template.
Yeah, so the question is, how does this overloaded work? Well, overload, forget about this weird using statement. That's just like kind of a workaround for a technical corner. Basically, overloaded inherits from all of its template arguments. Okay, so this overloaded is going to inherit from these two lambda types. Okay, and because it inherits from something that's callable, it's callable too. So it has an overload of the function call operator that takes a cat reference. So basically, overloaded lets me just inherit the callability of a whole bunch of callable things. In normal overload resolution of functions, we'll select the right one that I want. Now, you might say, where's the constructor to overloaded? Well, you don't need one because overloaded is what's called an aggregate type. It just has some base classes, no virtual methods, no methods really, and the like. So very simple types like that, you can look up the exact definition, are called aggregates. And the compiler will automatically synthesize a constructor if you just call it with the types of all the fields. And then class template argument deduction will grab the types of all the field. So all of these features, it's really cool, like they work together like magic. Okay, I think you had a question. Yes?
This looks kind of MLE, so it's like the standard linking with for getting force values.
No, I don't think so at all. The variant-based approach is not at all MLE, but one thing that's been repeatedly observed is compile time metaprogramming with templates is a pure functional language, right? And say if you look at Andrei Alexandrescu's modern C++ design book, that's incredibly influential. In effect, what he does is he embeds scheme, not ML, in the template instantiation system. Because what are the values that templates take? They're functions and types that can't be modified. You can't change the definition of a function. So compile time programming looks a lot like functional programming, because until constexfer was introduced, you didn't have variables. Now people are actually moving in the other direction, because it would be nice if compile time programming looked more like runtime programming. So there's still a place for traditional template metaprogramming, but for the most part, people are doing a lot more value-based constexfer programming that can hit constexfer variables that change their value during compilation. So, if anything, I'd say your question would have been spot on 10 years ago, but now things are moving in the other direction. Okay, I'm going to take one more question. You've asked several, so I want to ask first if anyone else has a question. Okay, go ahead.
So actually, there's two, but I'm just going to ask the main one that I would care about, and that's in the overload in the slide. Do you have to actually have it as an operator overload, or if your TS or your function actually is like, let's say that you call TS of a full function that takes like a number structure and wants to value.
You don't need all of them. So I could put an auto reference in here or anything that will work, but I can't use an ordinary function because an ordinary function is not a.
I was talking about one on the top of your struct overload, wanted to kind of modify it so that yes, operator, so a function that based on.
Yeah, that's probably. Be careful you don't do a solution in search of a problem, right? Like, since I'm inheriting from all of these things in principle, I could go ahead, right, and make any assumption at all I want about what I inherit from, and then leverage that. But you have to ask to what end, right? So the clear reason here is I want to be able to create an overload set of callables. So that's what I do. There may be useful other applications for it, but you know, you don't want to try to like overload the ship with an overloaded template that's going to solve every possible problem. So there have been proposals proposals to add overload sets to the standard. And I think it would be great if one of those got adopted. There are technical challenges. Everyone loves the idea. As soon as that happens, then you can forget about overloaded and just throw the overload set in here. So this is a substitute for not having overload sets. So you could do the kind of thing you said, but you have to know what problem you're solving with it. And it's not clear to me what it is. Anyway, I think we've gone a little over time, although I'm thrilled that there were so many questions. But so I think I'll go and call it right now. Hand it over to Ryan.